what we're going to do is we're going to look at a general overview of the different types of intermolecular forces, or what intermolecular forces are. And then in the class, we will be looking at these in more detail and, more importantly, looking at their implications. Now, intermolecular forces, from this point on known as IMFs, are the forces of attraction that occur between molecules. Okay, so between molecule A and molecule B. They're weak compared to our intramolecular forces, and our intramolecular forces are the forces which hold a molecule together. And we've already talked about our types of intramolecular forces, which is our ionic, due to the electrostatic attraction between ions, our covalent bonds, which can be divided into our polar covalent and our pure covalent bonds. Those are within a molecule. Between molecules are the attractive forces, which we call intermolecular forces, or IMFs. They're much weaker. Okay, now for us there are three main types of intermolecular forces. There are what we call London dispersion forces, or LFs. There are dipole-dipole attractions, and there's a special type of dipole-dipole attraction, which is called a hydrogen bond. Okay, we have to be careful. Even though the word bond is there, it's not a bond. It's an attraction between molecules. So our London dispersion forces, the London dispersion force is the weakest one. It exists between all molecules, and it's due to the shifting electron cloud of the molecule. So if the cloud of one molecule causes the electron cloud of another molecule to shift, it causes them to form temporary, slightly positive and slightly negative ends, which allow the two molecules to be attracted to each other, but it's very temporary. The electrons don't like to be pushed around, so they flip back to their normal spot, then they cause the other molecule, and so it's fluctuating as due to the attraction of the electrons, changing each other. It's sometimes called an induced dipole-dipole attraction. One of the things we want to note about our London dispersion force: the larger the molecule, the greater our London dispersion force. This makes sense because my London dispersion force is a result of the amount of electrons that I have and the amount of protons that I have in my nucleus. More protons and electrons that I have, the greater attractions I can form between molecules. So the larger the molecule, the greater the London dispersion force, but it is still my weakest intermolecular force. Our second type of intermolecular force is what we call dipole-dipole attractions, which exist between polar molecules. Okay, and our dipole-dipole attraction is the attraction between the positive end of one polar molecule and the negative end of another polar molecule. Now remember, our polar molecules are only partially negative and partially positive, so therefore the slightly positive end of one polar molecule is attracted to the slightly positive end of another. So these electrostatic attractions, we know that they can be strong. All we have to do is look at an ionic compound. Ionic compounds are held together by electrostatic attractions. But the difference here is that because these are partial charges, they're not as a strong attraction as if they were full charges. And so we have to keep that in mind when we look at these. Now the last type of intermolecular forces that we have are what we call hydrogen bonds. And these are a special type of dipole-dipole attraction. And we have to be careful of our definitions. Students often get this wrong. The hydrogen which is directly bonded to a nitrogen, oxygen, or fluorine will have a high electron negativity difference. So as a result, its slightly positive charge would be greater than any other atom bonded to these three. And so as a result, this allows that hydrogen that's bonded to our nitrogen, oxygen, or fluorine to have a slightly positive charge, which will then allow it to be attracted to the lone pair electrons of a nitrogen, oxygen, or fluorine of an adjacent molecule. Okay? And so this is key. We want to keep this in mind. So for our hydrogen bond, let's take a look at this molecule. This molecule, called formic acid or methanoic acid, we can see that we have a couple of oxygens. Our oxygens each have 2 lone pairs. We have a hydrogen bonded to an oxygen here. This oxygen has no hydrogen bonded to it, and we have a hydrogen bonded to a carbon. Now, because my oxygens all have lone pairs on them, this means that they're capable of receiving a hydrogen bond. So a hydrogen bonded to an oxygen, nitrogen, or fluorine of another molecule can form a significant attraction to these lone pairs. This hydrogen, because it's bonded to an oxygen, is capable of forming a hydrogen bond, meaning it can form a strong attraction to the lone pairs of an oxygen, nitrogen, fluorine on another molecule. This hydrogen up here is bonded to a carbon. It's not bonded to oxygen, nitrogen, or fluorine, so therefore it cannot form a hydrogen bond. It does not have a strong enough electronegativity difference. So in class, we'll take a look at further examples of this.
So let's take a look at a couple of compounds to see what kind of intermolecular forces they'll have. So our first one is CH4, and as we said, the first thing that we need to know its Lewis structure. So, okay. Then after you know its Lewis structure, then what we need to do is we need to look at our central atom, and we see that as AX4. So that tells us its shape. But also, more importantly, we see that we have only carbon to hydrogen bonds. So if I look up my electronegativities, I know my electronegativity for carbon is 2.5. My electronegativity for hydrogen is 2.1. Gives me an electronegativity difference that's 0.4. So here I can see I have no polar bonds in this compound. So because I have no polar bonds in this compound, I'm going to say it's a non-polar molecule. And I don't even have to worry about its shape. And so because it's non-polar, the only intermolecular force that it will have is London dispersion forces. So here we have CH3OH. So first thing we need is its Lewis structure. Okay, now from this we can see that we have a carbon to oxygen bond, carbon to hydrogen bonds, and oxygen to hydrogen bonds. So if we look up our electronegativity differences, carbon being, again, carbon is 2.5, oxygen 3.5, that's right, and hydrogen is 2.1, we can see that this is a polar bond, because it'll be 3.5 minus 2.1. And we can also see this is a non-polar bond, and we can see that this will be a polar bond as well. So because I have polar bonds, I have to look at my shape. I also see here that I have not one, but 2 central atoms, because we said any atom with more than one thing bonded to it is a central atom. So carbon is a central atom, and oxygen. So around this oxygen, I have an AX4. And so if we look at our chart, that tells us that therefore the shape around this will be tetrahedral. And here I have an AX2E2. Okay, and it's AX2 because I have 2 bonds and I have 2 lone pairs. So therefore that tells me it'll be bent. So now I have to take that into account when I draw this molecule in terms of its Vesper diagram. So I know I can put, with my carbon as my central, I can put 3 things on the page. And so one of the things I'm going to put on the page is the oxygen, because it's another central atom. And then I'll put a hydrogen on the page. And then my carbon has another hydrogen bond to it that will come out of the page towards me. And another one going into the page away from me. And then I'll add my bend. Okay, and remember, not only are you going to be given the AXE formulas, their shapes, but you'll also be given a generic diagram that you can then transfer. Okay, and so now with this, I can show my polar bonds. So I have a polar bond that's going right here between carbon and hydrogen. carbon and oxygen, and it's going to go from carbon to oxygen because oxygen is more electronegative. And I also have a polar bond here that's going to go from hydrogen to oxygen. So since these don't cancel out, I'm going to have an overall polarity, something like that. I don't know exactly how it'll go together, but it'll be something like that. And so now, because I have a polar bond, which results in overall polarity, I know that I have my London force, because that's in everything, London dispersion force, my dipole, and also here's one of our special hydrogens, because it is bonded with an oxygen, and this oxygen has two lone pairs. This molecule can form hydrogen bonds, and because we have oxygens with lone pairs, it can receive hydrogen bonds. So we say a two-way hydrogen bond. And this would come into play when we look at its properties. Okay, let's look at one last example. And we said that any hydrogens in front are acidic hydrogens, and they're bonded to oxygen. So first thing we need is our Lewis structure. Okay. And so now, once we know our Lewis structure, we can now check our bonds to see if we have any polar bonds. So we have a chlorine oxygen and an oxygen hydrogen. So we look up our electronegativities. Chlorine is 3.0, oxygen is 3.5. So therefore we know between them we're going to have an electronegativity difference that's equal to 0.5. We said 0.5 is a polar bond. Okay, and then oxygen is 3.5, carbon we said 2.1. So we have an electronegativity of 1.4, so we know that that will be a polar bond as well. So as a result, we have to look into its shape to see if they cancel out. Again, we go back to our molecule. We have two central atoms because we have two things with more than one bonding to it. So this one here, I have an AX3E. Because our double bonds lie right on top of each other, we treat double bonds as if they're one bonding group. So I have one bonding group here, and one here. So that's why I have three. And then I have one lone pair on my central atom. Then I have a central atom here, AX2E2, because I have two bonding groups and I have two lone pairs. So when we look on our chart, we see that this is trigonal pyramidal, and this is bent. Okay, so now we're going to use our information that we're given. Again, because this is a central atom, I'm going to try and put it on the page as well as the other central atom. So with my trigonal pyramidal, I can have one on the page, and I'm going to have this oxygen on the page because it's also a central atom, and this oxygen is bonded to a hydrogen. And then I'm going to have my oxygen on the page, coming out of the page and going into the page. And we'll just show that's a double bond like this. Okay. And now we can show our polar bonds. So we know that there's a polar bond here, and it's going to go towards the oxygen. There's a polar bond here. It's going to go towards the oxygen. And a polar bond here. So we have three poles down in the chlorine, nothing up. So in the chlorine, I'm going to have an overall down. And I also have a polar bond here towards the oxygen, more electronegative. And it's going to go like that as well. Now you may think, oh, this bond can be freely rotated, and so this could stick up and it could cancel out. But because they're in different central atoms, they don't cancel out. Okay, so as a result, on this molecule, we have London forces, because they're in everything, London dispersion forces. Because it's a polar molecule, we have dipole-dipole. And then all of these oxygens here have lone pairs. So that tells me even if this hydrogen wasn't there, I'd be able to receive hydrogen bonds. Now with itself, it can't form them, but it could receive them. And so that'll be important when we look at properties. But because I have a hydrogen here, I can form two-way hydrogen bonding because I can both form and receive.